Welcome students. Today in this lecture series on lattice vibrations and phonones, we will be discussing lattice vibrations in one-dimensional diatomic chain of atoms. Now this lecture is in line with our attempt to understand how the elastic properties of solids affect the waves that propagate through it. In my previous lectures on one-dimensional monoatomic chain of atoms, I explained how the dispersion properties of such a solid vary with a hypothetical homogeneous case. Certain questions were raised and I tried to answer them during the lecture. If you have not gone through those previous lectures, I would advise you to go through those lectures as they stand to be the prerequisite for this lecture. So if we look into a homogeneous monoatomic chain of atoms, which we had chosen as our reference for comparison, we could see that a homogeneous monoatomic chain of atoms would look like this. Such a solid would have a dispersion relation omega that is equal to Vs times k, where we had already defined omega as the angular frequency, k as the wave vector, and Vs as the velocity of the wave. On the other hand, an inhomogeneous monoatomic chain of atoms would rather look like this. Inhomogeneous because the mass of the chain is not distributed uniformly. Rather, they are concentrated in the atoms. So the mass is concentrated in the atoms and the chains are assumed to be massless. So these chains are assumed to be massless, where these atoms are the regions where the mass of this monoatomic solid is concentrated. So clearly there is an inhomogeneous distribution of mass throughout the chain, and that is why such a chain is called an inhomogeneous monoatomic chain. So due to such a difference in the architecture of the solid, the dispersion relation changes and takes the form like this. If you plot omega versus k, that is angular frequency versus wave vector, it will be a straight line for a homogeneous monoatomic chain. So the curve will be along both the quadrants, as k can be positive or negative depending on the direction of the propagation in the solid. However, this omega versus k plot of an inhomogeneous structure would look like this. Physically, the linear plot, if omega versus k is a straight line, it resembles the fact that the speed of the wave, which is omega by k in case of phase velocity and d omega by dk in case of group velocity. So the speed of the wave in case of homogeneous monoatomic chain, whether it is a single wave or a wave packet, will be same because it is a straight line, and the slope of this straight line is same as omega by k value at any point on this straight line. So the speed of the wave in a homogeneous monoatomic chain will remain constant irrespective of the wave number or the wavelength of the wave. We know this k wave number is 2 pi by lambda, where lambda is the wavelength of the wave. What does it mean? It means that the refractive index of such a material is constant and does not change with the wavelength of the wave. Such a medium is called dispersionless medium. So a homogeneous monoatomic chain is a dispersionless medium. Now if you look into the plot of omega versus k in case of an inhomogeneous monoatomic chain, we can easily predict that the curve is not linear, at least for all values of wave numbers or wavelengths. For smaller k values, that is for waves of higher wavelength, the curve appears to be linear. This linear portion of the curve is shown by this dotted red curve, and this further becomes non-linear with increasing k values. Eventually the curve attains a maximum at which, so this curve becomes maximum at this value, and at this value you can see the slope of the curve is parallel to k axis, which means d omega by dk, which is the slope of this curve, becomes 0 at this point, same as at this point. What does it mean? We know d omega by dk is the group velocity of the waves, This means that the group velocity of the waves of such a wavelength and frequency will have a zero velocity inside the solid. So does it mean that the atoms stop vibrating? Answer is no. Omega by k is not zero. If you see at this point, we have a finite omega value and a finite k value. So omega by k is not zero. That means the phase velocity of individual waves, they are not zero. Where are these individual waves coming from? These individual waves arise due to the vibrations of the atoms. The group velocity d omega by dk at this point or at this value of omega and k becomes zero. But the phase velocity omega by k with which the individual waves that are generated by atomic vibrations propagates or travels is still not zero. And we know a wave whose group velocity is zero is called a stationary wave. There are many examples of stationary waves. In case of sound waves, musical notes are stationary sound waves. They can be created by reflecting sound waves off a surface such as a wall or a membrane. Now, each atom in this case is still vibrating, which creates individual waves, and hence this omega by k value, which is the phase velocity, has a non-zero value. But all the waves, due to the individual vibrations of all the atoms, they interfere and generate a group wave or a wave packet. And such a group wave or a wave packet having an angular frequency this and wave number this will have a zero velocity inside the solid. It can be said that it is not moving. Such a wave group is not. It simply means inside a solid, it is the wave group which propagates the energy. So if such a wave group is stationary, that means the energy is not propagated by that wave group. So in case of such a wave, the energy is not propagated through the solid, rather it is contained within the solid. Another important piece of information we can extract from the plot is that we cannot increase the speed of the wave to infinite limits. It can be easily seen that the velocity of the wave is maximum here. Omega by k value is maximum here. And as k value increases, k and omega value increases, the velocity of the wave decreases. The velocity of the waves we have already seen or discussed in our previous lectures that it is restricted by the elastic properties of the solid. Now sound waves, they have a low frequency range between 20 Hertz to 20 kilohertz. So from the plot, the curve, this can be considered as a low frequency range. And from the plot, it is evident that the curve is linear at low frequency. The Vs value which we are considering here is the velocity which can be resembled to these sound waves. And that is why this velocity Vs is often termed as velocity of sound for, as in this case, an inhomogeneous monoatomic chain of atoms. The maximum speed of the elastic waves one can have in the solid is the velocity of the sound waves within it. Now, as the frequency increases, it drops down to zero. The curve also predicts that beyond a certain frequency, let's say omega naught, no waves can propagate through such a solid. What does it mean? It means that if a high frequency wave is incident on a solid, then it will be reflected, will not penetrate or propagate through the solid. So you could see here how the atoms would vibrate in a linear monoatomic chain of atoms. At the highest frequency, the individual atoms are still vibrating, but their vibrations are such that lead to standing waves. And as you decrease the wave number, these standing waves, you can see these standing waves convert into a traveling wave where the energy is propagated from this end to this end by these longitudinal vibrations. If you further decrease the wave number, you see how the vibrations of the individual atoms changes. And when we approach to low values of k, where the dispersion curve is approximately linear, the vibrations of the individual atoms look like this. If we come very close to zero, they vibrate something like this. So for very low values of k, these atoms would vibrate something like this. Now these mode of vibrations can be well visualized in case of transverse vibrations. So if we switch on to transverse vibrations, you could see how the individual waves atoms are vibrating and their collective movements lead to generation of group waves. The energy is propagated from one end or to the other due to these collective vibration or due to the formation of this group wave. As you increase the wave number, the wave is still traveling, and this is how the vibrations would look like for slightly higher values of k. If you further increase the value of k, you would see this is how the vibrations changes. If you keep on changing, at this value, the vibrations would look like this. And if you approach the highest value, the vibrations are such that lead to generation of standing waves. So this is how atoms would vibrate, leading to generation of group waves in a monoatomic linear chain of atoms. So this is a monoatomic chain of atoms, the case which we had discussed in our earlier lecture. In this case, all the atoms are same and separated by massless spring along one dimension. Under equilibrium, these atoms are separated by a distance a. n minus 2, n minus 1, n plus 1, n plus 2 represent the atoms at respective positions. For example, the nth atom is at a distance Na from the atom which is placed at the origin. This linear monoatomic chain of atoms has been modified like this. In this chain, two different types of atoms are separated by equal distance a and are arranged alternatively and linearly along one direction, say along x-axis, as shown here. Now let one of the atoms, represented by the blue balls, has a mass capital M, and the other atom, the one represented by black dots, has a mass small m, such that small m is less than capital M, and they are connected through springs which are assumed to be massless, having a spring constant beta. Now this chain appears such that every atom of one type has its two nearest neighbors of another type. So the black dots are having nearest neighbors as the blue balls, and the blue balls are having nearest neighbors, the black dots. Such a representation is termed as diatomic chain of atoms. Now, with such a system, what are the questions we are interested in answering? First, will the dispersion relation change in case of diatomic chain of atoms, or it will remain the same as in the case of monoatomic chain of atoms? Second, if it changes, what would be the dispersion relation for such a diatomic chain of atoms? Third, how the range of frequencies or the frequency spectrum of lattice waves propagating through this solid is getting affected. Fourth, how this range depend on the elastic properties of solids, and so on. So let this be a diatomic chain of atoms. Under equilibrium, the atoms are separated by a distance a, while like atoms are separated by a distance 2a. Now, as discussed in the previous lecture, there could be two possible directions along which the atoms can vibrate. One along the chain and the other perpendicular to the chain. Vibrations along the chain lead to longitudinal vibrations, and vibrations perpendicular to the chain leads to transverse vibrations. The problem is restricted only to longitudinal vibrations, as we did in the case of monoatomic chain of atoms. That means we consider the case where the atoms are restricted to vibrate along the direction of the chain. Now let us take a picture of the vibrating atoms at any later instant of time t and assume that the arrangement of atoms at that instant appear to be something like this. Here also we have assumed that the atoms execute simple harmonic motion about their mean position along the x-axis, and we restrict our problem only to longitudinal vibrations. So if you look into the two pictures and compare, you will see that relative to its equilibrium positions, all the atoms have been displaced. So this is the equilibrium position of 2nth atom. It has been displaced here. Let the displacement, the amount of displacement of different atoms will be different. So this displacement is different, this displacement is different, and so on. This is because all the atoms are bounded by elastic springs. Let the displacements of the respective atoms are represented by these parameters. That is, the displacement of 2n minus 1th atom is u2n minus 1. Displacement of 2nth atom is u2n. Displacement of 2n plus 1th atom is u2n plus 1, and so on. So like in the calculation for monoatomic chain, here also instead of using the entire chain, we restrict the calculations only to a unit consisting of an atom connected to its two nearest neighbors. In this case of diatomic chain, there would be two different units. One unit would be like this, which consists of a lighter atom in the middle with the heavier ones as its nearest neighbors. Let us consider this unit where the 2nth atom, we assume it to be the middle one, having 2n plus 1th heavier atom and 2n minus 1th heavier atom as its nearest neighbors. They are connected with 2nth atom with the help of massless springs. Similarly, the other unit can be considered as this one, where now the middle atom is an heavier atom, that is the 2nth plus 1th atom, which is connected to two lighter atoms, 2n plus 2th and 2nth atom, by massless elastic springs. We are supposed to find out the force experienced by these central atoms in these two units. Since these atoms are connected by elastic springs, so the net force experienced by these middle atoms will be the net spring force experienced by or generated by these two springs. If U is the displacement or be the elongation or compression in a spring of a spring constant beta, we know then due to this compression or elongation, a net force will be exerted by that spring, and that will be given by an expression F is minus beta U. Since the 2nth atom is attached to the 2n minus 1th atom and 2n plus 1th atom by two springs, it experiences two opposite forces, each one of which is proportional to the net displacement of the corresponding springs. The net force experienced by this 2nth atom due to these two springs can be expressed as this. Now, this is the net displacement of the right spring and this is the net displacement of the left spring. Now, since both the spring forces are in the opposite direction, so we put a negative sign here. We further simplify this expression. We can, this minus becomes plus. So we remove this minus sign, make it plus here. And if we open the brackets, we can write this expression as minus beta u2n. Minus becomes plus. So we can write it as plus beta u2n plus 1. And then here it is plus beta u2n minus 1. And then this plus minus is minus beta u2n. So finally, we can write this as this. Here F2n is the net force acting on this 2nth atom, which is m times A, and A is obtained by doubly differentiating the net displacement of the 2nth atom with respect to time. So we write it as d square u2n by dt square. Similar expression can be written in case of the second unit. So here the net force experienced by this 2n plus 1th atom is F2n plus 1, which we write it as capital M times d square u2n plus 1 by dt square, because capital M is the mass of 2n plus 1th atom. Here we have written it as small m because small m is the mass of the lighter atom, that is the 2nth atom. So in the similar fashion, we can write this expression. This is the net displacement of the right spring in this case, and this is the net displacement of the left spring. Simplifying it further, we can write this expression as this, and these are marked as equation number 1 and equation number 2. Now these two equations will be solved for obtaining an expression for these displacements u2n plus 1, u2n minus 1, u2n, and so on. Both these equations, equation 1 and equation 2, are second order differential equations which have plane wave solutions. The periodic solution of equation 1 can be expressed as this. Here x2n is the position coordinate of this 2nth atom, and we know this x2n can be expressed as 2n times a, where a is the spacing between the atoms. So u2n is a times e to the power I omega t minus 2k Na. Similarly, the expression for the displacement of 2n minus 1th atom could be expressed by this expression. The displacement of 2n plus 1th atom can be expressed by this expression, and the displacement of 2n plus 2th atom can be expressed by this expression. From the expressions of u2n, u2n minus 1, u2n plus 1 and u2n plus 2, we could see that they have same k values. It is the wave vector of a particular mode of vibration which is propagated through the chain. The omega value of all these expressions is also same. Omega is the vibrational frequency of the wave which is being generated by the vibrations of the atoms. Now here we could see that this is the unit which is being repeated all along the chain. Now since it is these two atoms are a part of this same unit, and thus the vibrational frequency of both the atoms is assumed to be the same. These two atoms of this unit are of different masses, so both the atoms must vibrate with different amplitudes. Let these amplitudes of vibration be capital A and capital B for the atoms of mass small m, that is the black ones, and capital M, that is the blue balls. And that is why in the expression for U2n, which is the displacement of 2nth and also of 2n plus 2th atom, these are black dots having mass small m. The amplitude of vibration is written as capital A, while that of 2n minus 1 and 2n plus 1 is written as capital B. Now if we assume that there is no net motion of the system due to this longitudinal vibration, the center of mass of the unit must remain at rest or must remain fixed. We know that the condition for the center of mass of a two-particle system to be at rest is m delta u1 plus small m delta u2 is equal to 0, where delta u1 and delta u2 are the displacements of capital M and small m relative to its equilibrium position at any instant of time. Now, if you remember why we are doing this exercise, we are trying to find the dispersion relation of this diatomic chain of atoms. And we know the dispersion relation is the relation between angular frequency and wave vector or wave number. So this is the first time you can see we have introduced the term angular frequency and wave number in the expression or in our calculation. Now our job would be to find a relation between these two terms. If we could find a relation between these two terms, we are done with our problem. That is to find the dispersion relation of this diatomic chain. In the present scenario, these two terms are related to parameters like A, which is a structural parameter, that is the distance between the two atoms, capital A, that is the amplitude of vibration of these black atoms, and capital B, which is the amplitude of vibration of the blue balls. What we have to do is we have to express omega and k in terms of known parameters like A, small m, capital M, and so on. Parameters like capital A and capital B are not known. So our next job should be either to eliminate capital A and capital B from the expressions or to get an alternate expression of A and B in terms of these known parameters, that is small a, small m, capital M, and so on. If you look into equation 1 and equation 2, you will see now that we have an expression for u2n plus 1, u2n minus 1, u2n, and also u2n plus 2. All we need is to doubly differentiate the u2n expression with respect to time and the u2n plus 1 expression with respect to time. Then we can replace all these terms with their equivalent terms. This is the exercise we are going to do now. So, if we differentiate u2n and u2n plus 1 with respect to time twice, by first differentiating u2n with respect to time, we get this I omega comes outside. So, it is I omega, and this is the expression of u2n itself. If we doubly differentiate it with respect to time, we get I omega and another I omega. So, it becomes I square omega. And I square is minus 1. So, it is minus omega square a e to the power I omega t minus 2 kNa, or which we can write as minus omega square u2n. Similarly, the u2n, if we differentiate u2n plus 1 with respect to time, we get I omega times b e to the power I omega t minus k2n plus 1a. If we doubly differentiate it, I omega and I omega becomes minus omega square, and this is the term nothing but u2n plus 1. So now we are having an alternate expression for d square u2n by dt square and d square u2n plus 1 by dt square. If we now replace all the terms u2n plus 1, u2n minus 1, u2n and this d square u2n by dt square of equation 1, we get here minus m omega square u2n, that is this term. If you remember, the term here for equation 1 was m d square u2n by dt square. So in place of this, we write this expression. So we are getting here this minus m omega square u2n. And now we write an expression for u2n plus 1, which is this. u2n minus 1 is this, and u2n is this. Similarly, we could write the equivalent expression for equation 2. And this is the equivalent expression for equation 2. Here also, if you remember, for in case of equation 2, we are having this term as capital M d square u2n plus 1 divided by dt square. So we replace this term with this term, and finally we get this minus capital M omega square u2n plus 1. Now for this is the equivalent term u2n, this is the equivalent term, and u2n plus 1, this is the equivalent term. Now from this expression, we can take e to the power I omega t minus 2kna common, and from this expression we can take e to the power I omega t minus k 2n plus 1 times a common. This is because we know u2n is a times e to the power I omega t minus 2kna. Similarly, u2n plus 1 is b times e to the power I omega t minus k times 2n plus 1a. So taking this common in this expression, will cancel this factor from both sides. So this we will perform now. So if we do so, if we take the common in this equation e to the power I omega t minus 2kna, we get this expression. Similarly, if we take e to the power I omega t minus k 2n plus 1a common from the second expression, we get this. Now we cancel this factor from both sides, as u2n also contains this factor and u2n plus 1 contains this factor. So we cancel it. If we cancel it, we are left up with a here. So it is, this expression is minus m omega square a, and beta times b e to the power plus ik plus b e to the power minus ik minus 2a. I can bring this 2a factor out from the bracket. So I can write it as beta b e to the power plus ika plus b e to the power minus ika minus 2 beta a. We know e to the power I theta plus e to the power minus I theta divided by 2 is cos theta. So I can write it, this expression, as 2 cos ka. So similarly, I can write this expression, the second one, as 2 beta a cos ka minus 2 beta b. Now taking this factor on this side, I'll get an expression 2 beta minus m omega square whole times a minus 2 beta cos ka times b, that is equal to 0. Let us name it as equation 3. Similarly, we get another expression that is minus, I take this on the other side, so it is minus 2 beta cos ka times a plus this also on this side, so it is 2 beta minus m omega square times b is equals to 0. Let us name it as equation number 4. So we have expressed the parameters capital A and capital B as a set of linear homogeneous equations. Such a set of linear homogeneous equations have non-zero solutions of A and B only if the determinant of their coefficient vanishes. The determinant of their coefficients would look like this. Now, if we expand this determinant, we'll get this. That is, this multiplied by this minus this multiplied by this. So minus minus becomes plus, and so there is an extra sign minus over here. If you expand it further, we write like this: 2 beta makes it 4 beta square, and then here it is 2m beta omega square. Here it is minus 2 small m beta omega square, and then finally minus minus makes it plus, so it is small m capital M omega to the power 4, and finally this expression, that is minus 4 beta square cos square ka is equal to 0. Rewriting it, we divide the entire expression with small m capital M, so this becomes omega to the power 4, and then here the term containing omega square r, it is 2 beta small m plus capital M, minus minus makes it plus, so minus we take it common, so it is 2 beta small m plus capital M, and then we have divided it with small m capital M, so it is this, and then finally the term which is not containing any omega, So it is this 4 beta square by small m capital M 1 minus cos square k. 1 minus cos square k is sin square k. So we write this equation as this. If you look into this expression, this is a quadratic equation. And if you compare it with the standard quadratic equation, I could say that x here is omega square, a here is 1, b here is minus 2 beta small m plus capital M divided by small m capital M, and c is 4 beta square by small m capital M times sin square k. The roots of such a quadratic equation is given by this relation, that is x is minus b plus minus root over b square minus 4ac by 2a. Putting the value of b, a, c in this standard form, what we can write is x here is omega square. So we get this expression. This is the b term, a is 1 here, and this is the c term. Now we can take this 2 square makes it 4. So I can take from this 4 and this 4, I can take this 4 out. So this becomes 2 here. So if I remove this, I'll get a 2 here. So simplifying it, and here this minus minus makes it plus. So if I remove this, this becomes plus. So that is what is written over here. 2 beta small m plus capital M divided by small m capital M plus minus and 2 taken outside. So it is 2 root over beta small m plus capital M square divided by small m capital M whole square, and that's minus 4 beta square by small m capital M sin square k. Now here also I can cancel this 2 from the denominator. So we are left up with this term. Now in this term I can take beta outside. So I can remove this beta square, and from here also beta square, and I can take this beta outside. So doing it further, what we did is we bring this beta outside. So this is the expression, and if I bring this beta outside, and I can write small m plus capital M by small m capital M as 1 by small m plus 1 by capital M. So this omega square expression can be written as beta times 1 by small m plus 1 by capital M plus minus beta has been taken out from this root sign. So it is beta root over again this 1 by capital M small m plus 1 by capital M square minus this term, that is 4 sin square k a divided by small m capital M. Thus omega can be written as plus minus root over this term. Now since omega is angular frequency and only positive values of angular frequencies are physically accepted, so we ignore the negative value. So omega comes out to be this, and this is the relation between omega and k here, which is known as the dispersion relation. And if you can see, this dispersion relation involves parameters like a, small m, capital M, and beta. These all are structural parameters. Beta is the spring constant, which is nothing but related to the bond strength between the two atoms in the diatomic chain. If you compare this dispersion relation with the one which we achieved in case of a monoatomic chain, it looks like this. Clearly, here for a monoatomic chain, one value of omega corresponds to one value of, there is one value of omega for one value of k. But here we have two values of omega, one by putting this as positive, which we has marked as omega plus, and the other one taking this as negative, which we can write it as omega minus. So for one value of k, we can have two values of omega, omega plus and omega minus. We'll stop here, and in our next lecture, we'll plot this dispersion relation as an omega versus k graph, and we'll give you a physical interpretation of this relation. In this video, I tried to explain one of the essential topics of solid state physics. I will be happy to have your comments and suggestions about this video. If you like this video, press the like button, subscribe this channel, and press the bell icon so that you don't miss any notifications. Thank you.